So today I'm planning to finish up the series of talks on universal composability, and part of the reason for this is we'll see, as Dan alluded to last week, we'll see sort of this is kind of the first place where the theory really makes an interesting statement that's somehow deep in some sense about what this dummy adversary that we're discussing can do. And beyond here, the paper that lays all this out really starts to go into a lot of complicated details. The theory is not so much further developed as it continues with this sort of definitional approach, and it does so in such a way that it's not really used by other work. We just kind of leave it here, and the other work sort of just ignores the following details, and they're really technical, and I don't think they're especially enlightening, but I'll say a few words about exactly where the rest of the story would go if you were to continue reading the paper. I just don't think it's especially enlightening. So let's talk about this dummy adversary. So to refresh your mind, what we're building towards is we're gonna claim that there's an adversary that is, in some sense, the hardest to simulate. If you can simulate this adversary, then you can simulate any adversary. That's the statement that we'll make. And this simplifies the security statement a lot. It removes a whole layer of quantification. We no longer have to quantify over adversaries. It suffices to just fix the adversary to be the dummy. And the idea of the dummy adversary, I mean, I've written out what it does here, but the idea is very, very simple. It essentially just acts as a go-between between the environment and the participants in the protocol. It's just all the dummy adversary does is waits to get messages from the environment and sends those to whichever protocol machines the environment likes. And the reason this is the hardest to simulate is it gives somehow all of the control over what happens to the environment. So now when you try to simulate this, the simulator isn't making many, it can't really do a lot, because at the end of the day, it has to look to the environment as though it's just forwarding messages. So producing a simulator for the dummy adversary is the hardest out of all adversaries. That's the statement that we're looking at. And Dan brought up last week that there's sort of this curious condition here about the total received import and the security parameter K. I looked into this, and this relates to a comment I made last week. When we have this security parameter K, what we're saying is that a machine never starts unless it's got at most K import in its budget. And the idea of this is, it's just to, somehow we want to have a global security parameter that we want to take to infinity to make asymptotic statements. So we somehow allow each machine a minimum amount of time that it spends running, and this prevents a situation where a machine does almost nothing, and the theory gets quite complicated. So this condition really just relates to that. It's saying if nu here is ever smaller than K, then according to the security parameterization, it wouldn't run. So the dummy adversary, to follow this rule, just make sure that we make sure that when we specify it, we don't require it to run when it shouldn't. That's all that's going on there. It's still a bit strange, I think, philosophically, but that's what Canetti is trying to get at with this condition. So the rest of the definition that I have on this board is just explaining what it means to forward, right? The environment sends some amount of import, it sends a message and tells the dummy who to give it to, and that message itself comes with some more import. The dummy just sends that message forward, and whenever it receives a message, it just sends that to the environment. That's what the dummy is doing. Good. Okay, so let's return back to our situation, what we're trying to prove.
Sorry, I raised this board, but maybe you were planning to talk about it now.
Okay, not especially. It's all good. So the theorem statement is we've got two protocols. And the theorem is that pi UC emulates phi if and only if there is a PPT adversary S such that for all balanced environments, balanced PPT environments, it gets quite wordy. The execution of phi under the simulator S is indistinguishable from the execution of pi under D as the adversary. So D being the dummy adversary. So we're saying, in the forward direction, we're saying, well, okay, of course, if every adversary can be simulated, then of course, in particular, the dummy adversary can be simulated. Forward direction is completely boring. The reverse direction is saying, if I can simulate the dummy adversary, then I can in fact simulate any adversary. And that's what we're trying to prove, that reverse direction, which is more interesting. Okay, so I made a comment. I think one thing that was not entirely clear last week was exactly the setup for this. So let me state that the assumption or the hypothesis is that the dummy adversary is simulatable, right? So we assume that there exists a simulator SD such that if we execute phi under SD, we can't tell that apart from exec pi DE. So I'm calling it SD to sort of pick out, this is the specific simulator that we know works for the dummy adversary. And what we want to prove is that for all adversaries A, we can produce a simulator S such that the execution of phi under S is indistinguishable from the execution of pi under A. And we're going to use this SD that we assume exists to build our simulator S. So this is what I mean when I say SD is a simulator for the dummy adversary. This is what I said last week. What I mean is we're going to take the simulator that we know exists and we're going to build a simulator for an arbitrary adversary. Okay. So the picture was kind of like this. We have the environment that we are trying to fool into not being able to tell apart the worlds. And the simulator that we're building S will work like this. Inside, it contains an emulated copy of the adversary that we're trying to simulate, and also an emulated copy of the simulator for the dummy adversary. Okay, so we know SD exists and we know what it does, and we're going to simulate an instance of it inside. We're going to emulate, I should say, just to make it clear, an instance of it inside our simulator that we're building. And then there's the protocol participants, phi1 through phi(n). And this picture I'm drawing here is just to guide you on what's going on. The simulator is going to work by running the dummy simulator to talk to the party and the adversary to talk to the environment. So from the environment's perspective, it's talking to the adversary. From the protocol's perspective, it's talking to the dummy simulator. And this is how we are going to, simulate our arbitrary adversary, and we'll see why this should work. Okay? So, the simulator is, so the simulator, what it does is, when it gets...
You'll have to walk a bit closer to the board for the orb to go over there.
I see, yes. So the way it works is when it gets the message X with import N, when I write this in the second part of the pair, it'll be the import. we emulate the adversary on this message. And then the adversary is, maybe it tries to generate a message to someone. And if not, we just answer back to the environment. Okay. Yes, I have to admit I was planning on having this board up before, but that's okay, Dan. I can work around it.
Sorry.
Just, perhaps I should have taken a screenshot or something, but this is completely fine. This is fine. I will work with this.
It's also present in the history world through that portal if you really need it.
Ah, nice. That's very cool. Okay, so big picture, what are we doing? We have some adversary that expects to talk to protocol pi, and we have a dummy simulator that is able to talk to phi and make it look like it's talking to pi. So the dummy simulator SD, if you go look at the second board real quick, the dummy simulator SD is going to translate between pi and phi. Okay, and this is the idea that the environment, that from the environment's perspective, it looks exactly like the adversary is talking to pi, but of course we're arranging things so that it's actually the simulator talking to phi. Okay, so we emulate the adversary. If A is the message, well, the message was intended for pi, so we will run our dummy simulator to translate to phi. So this is translating pi, a message for pi into a message for phi. And then I said run, I mean emulate. Keep that in mind. I'm going to sort of mess with the language a little bit. If the dummy produces any messages, then we're going to forward it. If the dummy simulator produces a message, we forward them. Okay. So the idea here is the adversary is making a message for pi, that the dummy simulator translates this to phi, and any messages it produces, we just send. Okay. I've forgotten to write here. My apologies. I've forgotten to write here. This is what it does if it gets a message from the environment. Okay. And then the other case is if it gets a message, from the protocol, well, we're going to do almost exactly the same thing, but in reverse, right? We're going to translate now from phi to pi and forward that to the environment through the adversary so that the environment can't tell the adversary and the simulator apart. Okay, so the first thing we do, emulate our dummy simulator on X. This is translating now phi to pi. There's two branches here. So the first case, okay, let's suppose that SD produces a message. SD might want to talk to a protocol participant, or it might want to talk to an environment. So if SD sends a message to phi, forward it. Because remember, we're only emulating SD, right? If it says I send a message, then we do have to actually say, okay, I'm going to forward that message. Okay, and then the more interesting branch is what would happen here, right? It's the dummy simulator would send a message to phi, it gets a reply, and then either it sends another message to phi or it sends one to the environment. Okay. So the interesting case is if SD writes, let's say, a message M to the environment. Well, the environment thinks we want the environment to think that it's talking to the adversary, not to the simulator. So we have to use the adversary we have to emulate the adversary to translate it to the appropriate form. Okay. And then we've emulated our adversary. The emulated adversary either wants to talk to the environment or to pi. So we do sort of the same dance, right? If A sends a message to E, we forward it. Otherwise, if it sends I need another symbol, I'll call this M prime to pi. Well, we have to do the translation again, right? So we're going to emulate SD again. And this is the next step of the translation. Okay, so now we have all of the behavior that we need. We've specified every possible case. Simulator, first, maybe it receives a message from the environment. Okay, it's going to emulate the adversary. If the adversary wants to talk to pi, it's going to use the dummy simulator to translate to phi. Then, once the dummy simulator wants to send a message to the environment, well, we have to make it look like it's actually the adversary that's talking. So we'll emulate the adversary on whatever the dummy simulator produced. And in this way, we've specified all of the ways that information can flow. So now we just have to prove that this does what it's supposed to do. And last week I argued that it was polynomial time. The basic idea behind this argument was by fiddling with the import bounds, we can produce a polynomial that, that S, as we defined here, is bounded by. I'm not going to go through that again, but we got as far as proving that it's polynomial, probabilistic polynomial time. And now we have to prove that, in fact, S and phi is indistinguishable from pi and A. Again, if you just quickly peek at the second board, we're trying to prove this statement here. So we've proved at least S is a valid simulator. Now we have to prove that the distributions really are indistinguishable. Okay. So the way the proof does this is by contradiction. So I guess I draw a line under here. So we proceed by contradiction. And the idea is, let's imagine somehow that there was an adversarial environment such that our simulator doesn't work, okay? Suppose we have such that the executions are in fact distinguishable. Phi S and E is not indistinguishable from pi A and E. And what we're going to do is construct a particular environment that contradicts our original assumption that the dummy was simulatable. Okay, so I'm going to produce an environment that that cannot be simulated with respect to the dummy adversary, which is a contradiction to the assumption. Therefore, the two distributions must be indistinguishable. Okay, we construct.
Sorry.
Yes.
I just lost you. Could you just say that again?
Yes. Yep. So we're going to assume that for some environment, the simulator that we defined, for some adversary A and environment E, the simulator we've just defined does not in fact work. Okay, we're going to assume there's some pair of such things that distinguish our simulator from the adversary. Okay,
Okay.
What we're going to do is construct an environment ED that satisfies exec pi d ed equals exec pi ae. So in other words, the execution of the dummy with ed is exactly the same as the execution of our the execution with the claimed bad adversary and environment. And also that exec phi sd et equals exec phi se. Okay, but this would be a contradiction because what we would then have is an environment ED such that the dummy adversary with pi and ED is by transitivity of equality. Oops, wrong thing. What we would then have is an environment where we could tell apart the dummy from SD. And we assumed in the beginning that the dummy was simulatable. So we have a contradiction. Does that make sense, Dan?
Yeah, okay, that makes sense.
Yeah. So just following the transitivity of equality, we're going to produce an environment where if it existed, then we couldn't have simulated the dummy for all environments. And of course, it's a contradiction. Okay, very good. So let's go back to the first board. And this picture is going to look almost the same. So the idea is that we have our environment here, ED, and we have our protocol phi. And we have the adversary that the environment is working with. This is not A, because remember A was the adversary assumed to exist that contradicts the adversary that was assumed to exist that works with E to distinguish S and A. Okay. So the environment, well, it's going to emulate an instance of E, the bad environment, and an instance of A, the bad adversary. And the way it's going to work is the initial input is given to the environment. The environment is going to talk to the adversary, which is going to talk to, the environment is going to talk to the emulated environment. It's going to talk to the emulated adversary, which is going to talk to the real adversary, which is going to talk to the real protocol. And our environment is going to use the emulated E to talk to the real protocol. This is not the prettiest diagram I've drawn, but the relationship to the S that we defined, it's going to do the same thing, but from the perspective of the environment rather than from the perspective of the adversary. You could, if you can compare to the second board, we're sort of bracketing things differently, right? Here, ED is this blue box that I've just drawn on the second board. So the thing that we're constructing is by taking the adversary and the environment, whereas the thing that we constructed before S takes the adversary and the simulator is in one box. We're kind of re-bracketing things to define this environment.
A dumb question, but why is it ED if it is made up of E and A?
Yeah. So ED is going to produce exactly the same behavior as pi with A and E. ED working with D is going to produce the same behavior I have phrased this very poorly. I apologize.
Oh, it's an environment for D somehow.
Right, it's an environment for D. So let me redraw this. This will make more sense. So ED in the one world, ED is going to use E and A to talk to D, the dummy adversary. And the dummy adversary, remember, talks to pi. And we'll just draw pi as one box for simplicity. So in one case, we're going to have this going on. And in the other case, we're going to have ED using E and what was the statement that I made? Tracking all of these letters is super complicated. It's going to use E and S to talk to SD and Phi. So it's an environment for the dummy adversary. That's why it's ED. And we'll see from the definition how this works. Okay. So we define the environment, it gets input Z, right, at the very beginning. So it emulates E with Z. As an aside, if E ever halts, so does ED. So the emulated environment is sort of doing the driving in some sense. If the emulated environment halts, then ED is going to halt with the same output. Okay? Another thing that the emulated environment could do is try to talk to the protocol. So if E sends a message to pi, ED forwards it. If, on the other hand, if on the other hand, the emulated environment wants to talk to the adversary, so in the left picture here, the adversary would be D. Then, well, we have to use A to emulate the behavior, because remember the environment, so E produces the bad behavior when it's working with A. So we're going to emulate A to lift this bad behavior to D in some sense. So the first thing we do in this case is, well, ED emulates A with the same message, the same import. And once it's emulated the adversary, well, once it's emulated A, then A might want to talk to the protocol, in which case, whatever message it generates, it forwards it to the adversary. Now, to ensure that this can be done efficiently, we're going to use exactly the same trick. We're going to fiddle with the import. The import is going to be I equals I should say here the message will be xn, where n is the import. Okay, so the import that we're giving the real adversary is p pi phi. This is the polynomial that bounds both pi and phi of n hat minus p pi phi of n hat minus n, where n hat is the sum of the n's, right? So n hat is the total import that we've received so far. And this is going to give us exactly the same thing as before, where we can use this to reduce a polynomial that bounds ED. Okay. Now this is this is where the ED is different from SD. It's going to have a bypass state somehow. So when the adversary replies, sorry.
Can I just make sure
Yes.
that in point 2 here, the forwards A's messages to the adversary, EGD, right? Yeah.
Yes, exactly. To the real adversary, not the emulated adversary.
Yeah.
Now, recall, this is where it gets a little bit complicated. Recall that A is the thing that breaks simulation for D. So A, whatever A produces, is going to be an instruction to simply send a message because it breaks D. So it simply forwards messages. That's what it's going to do. So whatever D receives is an instruction to send a message either to Pi or to the environment. And so what we're going to do is, if D was supposed to talk to the environment, we're going to skip the translation through A and simply, sorry, I said this the wrong way around. What we're going to do is if D is forwarding a message to the environment, to the protocol, then we're going to do the same trick before, use A to translate the message back into one that we can handle. If, on the other hand, D is supposed to talk to the environment, we are not going to do this translation. And that's because it should just be forwarded straight to the environment. So we have a special state here where we keep track of whether we were supposed to skip the adversary or not. Okay. So if the adversary is meant to forward to the environment, ED enters bypass, and this is meant to be a state in the sense of a Turing machine. Okay. So now we know how to handle the emulated environment's behavior. Now we need to discuss what happens when ED receives a message from the adversary. So I do this on the second board. Okay, so continuing the proof, I'm going to leave the theorem statement up so that we've got it in mind. So
Sorry
when
to bug you again, but you'll
yes,
have to
I have to
walk a bit
move.
closer.
Yes.
I'm your exercise coach. Run, Eleanor.
Run. I was T-posing earlier. There was a bug. It was very funny. Okay, so when it receives an output from the adversary, so the adversary is finished interacting with the protocol, and now it's ready to hand control back to the environment. So if ED is in bypass, I don't know how to phrase this other than to say it's like a break statement in C. It's just going to go straight back and emulate E in exactly the same manner as before. Right, so it's like we break this case and go to the previous one. Okay. I should say with the output. Okay, so if we were waiting for the adversary to forward a message to the environment, and now we got this message that's supposed to be forwarded, we're not going to do anything fancy. We're just going to immediately start running, emulating E again with that output that it was supposed to receive. Otherwise, we emulate A to translate in the same way as we did for SD. Emulate A on the output. And continue. Okay, so now we've handled all of the ways that ED interacts with the adversary. Either it's started and then wants to send a message to the adversary, to the protocol, which we handled, or to the adversary, which we handled, and now it knows how to handle all messages it gets from the adversary. So what happens if we get a message from the actual protocol? This is the direction we haven't done yet. From protocol. Well, E knows how to handle a protocol, so we'll just emulate E on this. Okay, so the picture is, if we get a message from the protocol, we emulate E on it. If we get a message from the adversary, if it was supposed to be sent to the environment, we emulate E on it. Otherwise, we use A to translate it to a message for E. Okay. So the first thing is ED is balanced. So recall that balanced means it always gives the adversary at least as much import as everyone else. So the proof of this is ED never gives I have to practice these boards more, I think. So ED never gives any more import to the parties than E would. To protocol than E would. And it always gives at least p pi phi of n hat. This was the condition about how much import we give the adversary. Always gives at least as much import as A would get. Okay, so since E is a balanced environment and ED never gives more import to the protocol than E, and it always gives at least as much import to the adversary, it's balanced. Okay, I guess I've just noticed that I haven't formally argued that it is in fact polynomially bounded, but you can arrive at this by the same argument, I guess. It's really just doing whatever E and A would do, so it can't be somehow that much worse than what they do. Okay, and the last thing is we want to argue that these distributions are equal, so they really do have a contradiction. So I'll do this on the third board. Okay. This is like playing Operation, trying to steadily erase. Okay, so the first Operation, you know the game. I have to use the tweezers.
Shocked if you touch the edge.
Exactly. Yeah. Okay, so we're going to show this first equality: xsec pi d ed equals xsec pi a e. Well, the argument for this is that ED emulates A, and also ED only uses the dummy adversary's functionality. All it's doing is using D to send the messages to pi that A would have sent anyway. So in other words, the messages that make it to the party are exactly the same messages that A and E together would have sent to the parties. Therefore, also, it halts whenever E does and outputs whatever E would, so the executions are in fact identical, they're equal, because it's just by construction it does exactly the same thing. Okay? So the last piece of the puzzle is the other equality, exec phi SD ED equals exec phi SE. Okay, so let's consider SD, the simulator for the dummy adversary, connected to ED. And recall that ED is composed of an instance of A and an instance of E. And the connection is sort of like this, right? So if we look at what happens along this wire, so to speak, the interaction between ED and SD, well, we see that this is in fact exactly the same as what happens when S talks to E. Okay, so remember S was this picture composed of SD talking to A. So S talking to E is the same thing as SD talking to A talking to E. So this argument is really, it's sort of at a, it's not at a strict logical level, but we're just saying it's the same picture, right? We're doing proof by diagram, but this diagram is not commutative. So because ED emulates A, and in fact S connected to E is the same as SD connected to ED, just by construction, they are in fact exactly the same transcript doing exactly the same thing. Did that make sense, Dan, or do you need to explain it again?
No, this part I think I follow.
Fantastic. So we say we have a contradiction. And we call it a day. So the conclusion is that there is somehow a hardest adversary, and if you can show that you can simulate that, you're done. Now, contained inside this proof, which the rest of the paper goes on to sort of try to formally define, I think it kind of succeeds, but it does so in such a way that is really quite impractical, and so it doesn't ever appear in papers. But what the paper goes on to talk about is, okay, so now we know what secure emulation is. Now we want to define this substitution action that we use. We want to really formally define it, okay? We want to say, if I have a functionality f, which in some sense contains some piece pi, and we have that phi UC emulates pi, then we have, I'll call this f pi, because it's sort of some functionality that uses a thing called pi. Then we'll say, oops, f pi swapped with phi UC emulates f. I keep trying to write a finite field, f pi. Okay, so this statement, which is formalized in sort of a very unclear, complicated manner, it's just saying, you know, I can, if I know my functionality is, if I know my protocol is secure using a perfect crypto system, then it's still secure if I replace it with something that UC emulates a perfect crypto system. And this is what real papers practically use. They define everything in terms of perfect crypto, and they say, well, by these UC theorems, we can simulate the dummy adversary by replacing the real crypto with the, by replacing the perfect crypto with real crypto, and somehow this statement is supposed to go through. That's how it's used in practice. It's all about, so what we have is a notion of secure emulation, and then we say, okay, now I can emulate a part of my protocol, and if I can do that, it's still secure. And that's pretty much where the story stops. The work behind the idea behind the dummy adversary somehow is that we don't have to define all of our stuff case-wise by what the adversary could do. We just fix one adversary and show that we do UC emulate for this adversary, and therefore we can do pieces, and we call it a day. Okay, so I don't really have a nice way to sum up all of this in mind. I guess I'd say that this shows that really defining what it means for a system of algorithms to interact is really quite complicated. There's a lot of things that pop up, especially efficiency, what it means for these machines to interact exactly. And if you want to really have everything be a well-defined computation, then of course you have to define what it means for an environment to be in place, what it means for an adversary to be in place, what exactly these are. But a surprisingly nice thing that we get is you can fix certain pieces of this, and you can reason in terms of perfect pieces and then replace them with nearly perfect pieces later, and the security goes through. So this is really the start of the story of composable security. And what remains to be done is sort of working it in a way that can be held within one's mind. I think it's fair to say that all of these moving parts are quite difficult to keep track of. And my hope, as in my PhD and my work, is that somehow we can condense a lot of these ideas in a more abstract and cleaner way, that we can then choose whether we want to introduce these notions of interactive Turing machines as one instantiation, or if in some contexts we don't need to fix that particular model of computation. These are the questions I'm interested in answering going forward. Okay. So crypto is mathematical. We have these pieces, and what we're trying to do now is sort of understand this in more detail. I think that's my summary.
I would say that although there's a lot of detail, it's not like this was truly complicated. It's, as you say, difficult to keep in your head, but I think after... I certainly didn't understand all of this as well as I would like, but I got out of it a set of very valuable impressions, and one of them is that this is conceptually pretty straightforward. I mean, it's not trivial in terms of the amount of moving parts, but it's not crazy either. So I'm rather pleased and impressed that a system as conceptually simple as this. I mean, it's hard to imagine it being much simpler than this, really, if you want to talk carefully about interacting Turing machines and have some notion of the security parameter and all this. It's about as simple as it could be. So I think my opinion of the field has definitely improved after hearing this story.
I think what's kind of interesting as a cryptographer, I mean, especially talking to a community of mathematicians, is yeah, it's somehow conceptually what we're doing is really simple and in some sense dead obvious, right? Somehow it seems like it is obvious. But as soon as you scratch at the surface, yeah, all of these moving parts appear, and really trying to set them in a nice order, in a nice story, is suddenly very, very difficult. Yeah, it's sort of strange how crypto rides the line between being so simple it's almost trivial, but then to actually do it reveals all of this hidden complexity. And that's certainly true if you analyze like the actual practical security proofs of crypto systems and so on. It doesn't take very long before you're looking at esoteric algebraic number theory papers trying to understand why a thing works. So I think crypto is really, it's sort of really fascinating how it has this aspect to me.
It seems like it's not unusual for young fields to look a bit like this. It takes many generations of PhD students
Yeah.
digesting things and simplifying things, and eventually it looks kind of obvious and neat, but I think it's not.
Yeah,
If you look
yeah, I
back at the
mean,
history of even algebraic geometry, my field, in the olden days, it was pretty incomprehensible.
I think I often compare to, because I'm a physicist by undergrad training, right? I often compare to the picture of classical mechanics that we have. You look at Newton's laws and you're like, oh, this is easy, right? There's just, okay, we have conservation of momentum, and we have this point about the relationship between momentum and acceleration. Easy, right? It's very straightforward. But on the one hand, this is the hindsight of over 300 years of mathematical work on classical mechanics. So of course the story is simple now because we've figured out how to tell it. And on the other hand, as soon as you introduce, a double pendulum or the three-body problem, these simple rules produce all sorts of crazy consequences that you have to think through carefully. And then we have tools like Lagrangian mechanics to tame those. And I kind of get the impression that crypto doesn't have the tools like Lagrangian mechanics to really tame the thorny stuff yet. Okay, so what we've done in this first season, I guess, is take a high level view of interacting systems and what it means for systems to emulate other systems in a secure manner, and therefore how we can produce statements about something as complicated as dozens of machines running through the internet. What I'd like to look at, maybe I take a break for I take a break for the next, say, 4 weeks or something. And then what I'd like to do is talk about the thing that really got me into crypto in the first place, which is the study of zero-knowledge proofs. And this will be much more sort of crunchy in the sense that we're going to have to look at, a bit of group theory and complexity theory proper. And what we'll get out of it is I'm going to build towards this quite shocking result that every NP relation has a zero-knowledge proof. This is a famous result in the area of zero-knowledge proofs, and the idea is simply, I can prove to you that I know a witness for an NP problem without revealing any information at all about what that witness is. And this may be, if you're into complexity theory, this is maybe motivation enough on its own. But in practice, what this means is things like voting protocols that are being worked on. You can prove that your ballot is well formed, but no one knows who you're voting for. You can prove that you've successfully shuffled a list of votes without revealing to anyone the relationship between the two sides. And the way this is used is you might have a list of voter IDs and encrypted votes, and then I'm going to shuffle all of these so that I encrypt the IDs and then later decrypt the votes. But the shuffle is done so that you can't tell which row, right? If I didn't shuffle it, you could just go row by row. Oh, this ID corresponds to this vote after the decryption is done. And what you can actually do is shuffle a list like this and prove that you didn't add or remove any elements, but have it so that no one can tell what the shuffle was. I think this is one of the most exciting things you can do in practice. It's like, how does this even make any sense, right? Like, how is this even possible? And yeah, I want to take a close look at how we build up this field, and how we do these. I like to call them magic tricks. It's like a sleight of hand magic trick. It's like, where did the Queen of Hearts go? It just disappeared. And yes, we can prove that you can do this and that it works. So that's where I'd like to go after this.
Oh, that sounds excellent. Well, thanks a lot, Eleanor. I learned a lot from this, and looking forward to the next installment.
Great. Thanks, Dan. Very pleased to be here and chatting. It's lots of fun. All right, I'll see you guys around. Have a good one.